Hello everyone. This is a short video about the Mach's principle, what it is and how it at first inspired Einstein to create general theory of relativity, that theory of gravity, and later made him be disappointed in it. So first of all, even if you don't know anything about physics and never studied it, most of this video will be accessible to you. I'm trying to emphasize that just to show how fundamental these questions actually are, in a sense, how basic they are, so that anyone could ask them and think about them. And yet, not everything in them, in these questions, are clear to us yet, even today. And however, the interesting comment to make here is precisely that if you actually studied physics in, say, university somewhere, you probably only heard about this Mach's principle, but never actually understood what it was. It was something very confusing, and the lecturer probably kind of glossed over it very quickly without really explaining it or putting attention to it. And for the reason being that philosophical questions are in general neglected in our teaching of physics today. They're kind of considered unimportant for calculations and only serve as historic explanatory purposes. So that's why you probably have some sort of deep unsatisfaction with this question. I mean, I will try to resolve it today. However, well, I don't know whether you like it the way I understood it. As I promised, I will start from the basics. So I'll start from Newtonian view, which everybody will be able to understand intuitively. And then I'll show where people start to deviate from it. Okay, so I hope you could see my screen. I'll be drawing pictures, so it'll be easier. So let's start with, general, our first steps in physics. um, well, in the Newtonian life, right? So let's say we sit in our lab somewhere on Earth. We have a table, and we just make simple mechanical experiments on it. We have metallic balls, and we could collide them. They hit each other. We know their masses. We could measure the velocities using clocks and rulers, right? Yeah, and knowing distances and times, we could calculate velocities and accelerations. And we could try to induce some laws of this ball's motion. For example, momentum is conserved, right? And this in particular means, if you don't know what momentum is, let's say if a ball is sitting still on the table, it will remain still unless you act on it by some external force. And also, yeah, here is where Aristotle, who was the first person to think about it, made a mistake, already made a mistake. Yes, he had a theory of natural places. So he just concluded that the object sitting still is just a natural place for it. So he saw that you need to actively push on to the object to make it move because of that. Whereas whereas actually, in fact, we know that object which moves at constant velocity with respect to the table v would continue to move this way indefinitely unless there is a force acting on it. So Aristotle's mistake was only corrected by Galileo Galilei 1,000 years later, which is ironic. Yeah, he realized he was the first to discover this property of inertia. Now, another important observation which Galileo also made, that in fact you cannot really distinguish systems which do not move with respect to Earth and system which move with respect to Earth with constant velocities. So yeah, if we make a copy of our lab and put it say on a train or something, on a car which move with respect to Earth at constant velocity v, yeah, and we make all the same experiments here. With these balls. There will be no way to tell what this velocity v is. So that's, you could say, is the first version of the relativity principle, which was later elaborated on by Newton and integrated into his formalized and integrated in his three laws of dynamics, but first discovered by Galileo Galilei. So yeah, this discovery led to the eventually, again, it wasn't even done by Galileo or Newton himself, eventually led to introduction of the notion of inertial frames, which are frames where the laws of inertia holds. In other words, the objects moving at constant velocity will continue to move at constant velocities unless the forces act upon them. Yeah, and the reason why it was somewhat counterintuitive for people like Aristotle is because there is always dissipation and friction involved here. So the force of friction is what actually stops the ball in real life. Yeah, and now you may ask, well, I was talking about Earth, right, here. And I was using Earth as an example of a basic inertial frame. But the truth is, first of all, Earth is neither an inertial frame, nor we need a special single out one. So you know that Earth is technically rotating around its axis. It's also rotating around Sun, so we could actually detect it using special experiments. You could detect rotation around its axis using Foucault pendulum, for example. Yeah, but it's like good enough approximation of an inertial frame. What's more important is that what we care about is a relative relation between different inertial frames. This was the first time where you could say the concept of absoluteness of space was challenged. And we'll see further how Newton struggled with it, and why he actually believed in absolute space. Okay, but for that we need to contrast inertial frames with, well, something else, right? The non-inertial ones. So Newton's view was that, let's say, if the train starts to move with acceleration, with respect to Earth, so its velocity is not constant. This means it has to turn the engine. The experiments done on board will actually reflect it, and you know what will happen. Yeah, the balls sitting on the table will start to move backwards, and you could feel it when you sit in the car. You press the gas pedal. What you feel? You feel you pushed back, right? So that's an example of non-inertial frame. In fact, you could say, well, when I say that Earth is an inertial frame, is it actually true? Well, we know that Earth is rotating, so we literally could test it using Foucault pendulum, and it also moving around Sun, and also maybe through the galaxy, right? And yeah, this is all the right question. So strictly speaking, no, Earth is not exactly inertial frame, and we could test it using these experiments. It's a good approximation, at least in Newton's view. Yeah, but this raises important problem, right? It raises the question of absoluteness of acceleration. Newton indeed thought that acceleration is absolute. You see that you can tell whether you're accelerating or not. So you cannot tell. You see from this experiment, we see that you could not tell whether you're moving or not with constant velocity. So the movement is relative, velocity is relative. But with acceleration, it seems like you can. Imagine, to prove that Newton come up with the following experiment. Let's say you're floating somewhere in outer space, far away from all other objects, and you're holding a, I don't know, a spring, and a ball on a spring in your hands. Then you could see that, say, if you rotate the spring in one direction or another, you can tell whether you're moving with acceleration or not. You could tell if in one direction the spring contracts, gets compressed, and compared to other ones, this means you're moving with acceleration in this direction. Yeah, and again, you will feel it with your own body too, right? So Newton originally used a water bucket experiment and rotation, right? So if you will be rotating like this, there will be centrifugal forces acting on the spring too, so it will stretch. And Newton famously used the bucket experiment. It's not with water. The water will react to centrifugal force as well. It's not completely accurate because it relies on the gravitational forces. So instead, you could say the correct Newton experiment would be if you have a ball of water floating in space, right? It will be spherically symmetric if it's not rotating. But if you start to rotate it, you'll get squeezed like this, become ellipsoid. And no matter whether you're stationary here and observing it's rotating, or you're moving with respect to it, you'll be able to tell whether it's rotating or not. It will either look like this, or like this. Yeah, and this experiment actually led Newton to introduce the notion of absolute space, make Newton believe in absolute space, because his view was that, look, it seems like there is no other bodies around, and you could still tell whether you're accelerating or not. How could you, like, that means there has to be an absolute space. What you're accelerating, you just with respect to what you're accelerating. Well, I don't know how to say it, but what you're accelerating with respect to. Yeah, that's probably correct grammar. There has to be something, and he saw that therefore there has to be an absolute space. So that is Newton's logic. Acceleration is absolute, and it's absolute with respect to the absolute space. That was his view. Now, well, moving forward, I should say that even at his time, his greatest opponent, Leibniz, already disagreed with it. He said that, well, no, actually, all motions are always relative. That's what we always observe. You can't observe motion with respect to something other than other objects. There is no absolute space because of that. In fact, Leibniz has used his own philosophical principle, which saying that something like, well, or simplifying it, you shouldn't multiply concepts without necessity. And if you don't have any observable reasons to introduce absolute space, you shouldn't have it, in a sense. So some kind of logic like this. And this idea was actually later developed by Mach. So what Mach said is that in this rotating bucket of water experiment, or just pair of balls, right? Pull apart. What's happening is that that indeed the forces you feel, the centrifugal forces, are somehow caused by all other matter in the universe. Now, this is this famous Mach principle, which looks so weird, right? What does it actually mean? So what and how he come up with it? And this is actually follows from the assumption of the absence of absolute space. Let's consider this setup properly. Let's say you have your body, or you say you have this ball of water or a bucket, or this chain of balls as one system. Let's say it's you, and you have like a shell of matter around you, which will be modeling our distant stars, all other matter in the universe. It's different stars. Far away from you, right? So now imagine two scenarios. In one scenario, you start rotate with angular velocity omega, say with respect to the stars, and you kind of feel centrifugal forces, right? It raises your hand up. Well, up. We don't have up, so but in everywhere, somewhere far away in space. But the thing is, the squeezing of the water, of the ball of water, will happen. And this is from one point of view. And there's another point of view. You could say, Mach says, well, okay, if there's no absolute space, this situation is physically indistinguishable from a situation where you're not rotating. You're staying still, but all the stars are rotating around you, right? In the opposite direction. So yeah, the only way to distinguish the situations would be if there is some absolute space, and then you could tell. But actually, there is none in his view. So there has to be the same. And this means, from this point of view, somehow these rotating stars should do something which would make you feel like your arms race. Or, you know, the ball of water squeezes. That's what he mean by his idea that the reason why when you start spinning around and feel like your hands raise up, it's caused by this distant star somehow. It's just immediate consequence of rejection of the notion of absolute space. And this idea is what inspired Einstein so much. Yeah, he was hoping that proper understanding of gravity will allow for this effect. But let me show you what Einstein actually did, more like a step-by-step way. So first of all, yeah, he questioned the Newton's nature of gravity. Remember when I said that, well, Earth is more like a somewhat inertial frame, almost, right? Einstein questioned that because, well, he said, if you sit in a lab and you do the same experiment with accelerometer, which is basically a spring to attach to a ball, you rotate it, you will see that this spring compresses, right? When you rotate it. Oh, sorry, oriented vertically. Newton thought about it as a force of gravity acting on the ball, right? But Einstein said, well, gravity is a bit weird force. Just think about it. Whenever any other force acts on us, you know, when somebody is pulling you on the rope, you feel it, right? You feel acceleration. You know, or when you're in a car and the engine pushes you, right? Or in a plane. And you understand that you're not in non-inertial frame. But when you're pushed by gravity, in a sense, it means when you're falling down on Earth, during the moment of the free fall, you don't feel anything. So it's very different in a sense. It is precisely when you are weightless. If you do this experiment with accelerometer while you're falling, it will give you negative result. It will be acceleration. Well, it will measure zero in all directions. So it seems like the free falling frame is the inertial frame. And when you're standing on the ground, that's when you feel like the ground is pushing you up. Like if you're accelerating, like, you know, in a rocket, but it's very weak one, right? You just feel like what's happening. There's the ground pushing on your legs and legs pushing on other parts of your body, and you feel it in your bones and you're everywhere, right? So in Einstein view, it seems like this should be the inertial frame, right? not the planet. So because locally here, you could do all the experiments with the balls and so on, and momentum will be conserved and so on, just like Newton wanted. However, there is a problem with it because, well, if you look further away, if you look at the surface of the planet, you'll see that you're falling down, and the Earth is somehow moving at you with acceleration. And if you look at distant stars, they're also for some reason moving towards you with acceleration. So that's how you realize, well, no. Actually, this is not an inertial frame after all. Yeah, that all of that led to the following two developments by Einstein. First of all, he tied acceleration to gravity, and gravity is the geometry of space-time. So he said, like, well, if you in free fall locally, you feel exactly like if you're floating in the free, far away space. This means that the gravity is not really a force. It's just the geometry of space-time looks like that you're falling towards gravitating bodies, massive bodies. Inertial frames were replaced with this notion of local inertial frames, where, yeah, when you're free falling locally, you could still do all these experiments and feel like you're not moving. But if you look further away, that's when you start to see that other stars are moving with acceleration, planet is moving with acceleration, and there is no force acting on them. So by Newton's definition, this frame is also not inertial. So in Einstein picture, it has geometric meaning. In Einstein theory, right, we have this four-dimensional manifold, which represents space and time. So in a sense, you could say, well, this is kind of weird because Einstein was trying to get rid of absolute space and time. And yeah, I'll explain what the problem is. So yeah, he has to introduce them, this mathematical concept, initially just as auxiliary notions for convenience of mass description. And gravity is encoded in the geometry of the space-time, in the distance function between 2 points, any 2 points. And massive bodies, they could alter this geometry. So this Earth is somehow, squeezes this grid. Like this grid is rectangular, but the planet will curve it inward like this. I don't know how to draw a three-dimensional picture, but in 2 dimensions, people usually draw it with a rubber sheet analogy. I made a separate video about it if you want. So anyway, Einstein was hoping that this will allow him to satisfy the Mach principle. So we can go back to our setup with massive shell. Yeah, so in that sense, we see that what exactly is local inertial frame here is determined by the metric around you. It's the frame in which metric is locally flat, right? Like in a distant universe, far away from gravitating bodies. But in which coordinate frame it will be flat is determined by massive bodies around. So we have a hope to satisfy the Mach principle. So Einstein thought that indeed now when we have this rotating stars around you, because of the movement, the gravitational field which they induce on all other points of space-time, I don't know how to draw it, when they're rotating, will affect you in such a way that your arms will be pulled towards sides, right? And yeah, people solved this problem in the simple setup. And what they found is that at best, depending on the mass and configuration of the shell, you could produce like 0.8, well, 80% of the standard Coriolis force. So it's not exactly what Mach wanted or Einstein wanted. So it's like the situation when you're rotating, you will feel the Coriolis force with the corresponding angular velocity, omega. But if the shell is rotating, you will only feel this much less. So they're physically distinguishable in Einstein theory. And Einstein was kind of disappointed with it. He felt like that's all, I kind of failed. This means my theory has absolute space after all. And indeed, in this setup, it kind of had. There is some problem here, which I haven't talked about it. When you're solving these equations, Einstein equations, which determine the metric in the whole space-time depending on mass distribution, you have to fix the boundary conditions as well. And if at the boundary you fix the metric to be proportional, mean equal to the flat space-time metric, then you will get this effect. So what it does is that it provides an infinitely far away rest frame, which is like bind to attached to our universe by nails, in a sense. You freeze the space-time fluctuations on infinity, which is kind of unphysical. So it's almost like there's some infinite negative mass at infinity freezing, or I mean not negative, I don't know what exactly it is, but freezing space-time to be constant. So it's hard to explain, but this literally means, like, imagine there is our universe embedded in this kind of cup, and it's look like this sheet, right? I'm using this two-dimensional analogy, and you said, oh, I freeze it to be flat here at the boundaries, and this is my massive shell, and when this shell rotates, it bends the space-time like this, right? And when it rotates, it drags the space-time inside with it to some degree. However, because this boundary is fixed by nails, pinned down like this, it's not rotating with exact velocity omega. So it still feels some of this reference frame here. So this is the, you could say this was unphysical effect. And in fact, today, most people think that for our universe, for physical universe, where we have matter filling it homogeneously, not as a shell around you, but all the way to infinity, right? There's matter everywhere, like this. and there's no really boundary, and it's not the universe is not frozen there to be flat, the Mach principle is indeed satisfied. So that the rotation of this whole universe, which has enough mass in it, will indeed produce the Coriolis forces, the analog of equivalent of Coriolis forces, like if you rotate in respect to it with velocity omega. So, I mean, I saw some papers about it. I haven't checked them myself, but that's a claim. A lot of people, I think, believed it. So in a sense that it seems like Mach principle is correct after all. But that's for some reason didn't satisfy Einstein. Einstein wanted the Mach principle be automatic in any geometry in his theory, which is a bit strange. And in fact, this is very curious because it raises questions about the status of general relativity. So general relativity, in a sense, has absolute space in some geometries, which we might consider unphysical because of that. But in our world, it acts like if there is no absolute space. It describes a universe where Mach principle is satisfied, supposedly. Yeah, and again, this raises the question about whether, again, general relativity is, in fact, the optimal description of our universe, or it's kind of redundant because it describes our universe and infinitely other non-existing unphysical universes with absolute space, or there has to be a more optimal description. And the question about ontological nature of space-time. If, it looks like in our universe, which is, again, even described by Einstein theory, the Mach principle is probably satisfied, there has to be a description without absolute space, and therefore maybe there is no absolute space indeed after all. But then what other gravitational waves? We actually detected them. And we think, again, according to Einstein theory, that gravitational waves are precisely the ripples of space-time. There are these ripples wave traveling away from, some gravitational event. I mean, some, collapse of two, I don't know, black holes into one, which produces ripples, which is traveling away from them. So it seems like the fabric of space-time has to be real in a sense. Yeah, as you could see, not all questions here are answered, and there are still a lot of things to think about, even if you haven't studied physics yet. So I hope you enjoyed this video. Maybe it clarified something about Mach principle for you, and I hope it might inspire you to think about these questions more deeply. I'm certainly not the best person to do it, but see you next time.